We are on page 14 and we are going to continue talking about sound. Properties of sound waves. The back and forth vibration of an object creates the compression waves of sound. The motions of a loudspeaker cone, a drum head, and guitar strings are good examples of vibrations that cause compression waves. From the video we watched last time, that included the band Metallica playing as part of it, we saw different instruments and how they vibrate to cause a sound. All musical instruments have to vibrate to generate some type of sound, because without a vibration, there cannot be any sound. This is different than the up and down or transverse motion of a water wave. Remember, sound is not a transverse wave, it is a longitudinal wave. So at the top, something we've already discussed, that a longitudinal wave still has wavelength. Since the definition of wavelength is the distance between two successive points, then the distance between one compression and another can be taken as the wavelength. You can also take the wavelength to be the distance between one rarefaction and another. In the case of sound waves, they travel by the vibration of air particles. And here we have a diagram showing a loudspeaker on the left, causing air to vibrate until it reaches your ear. The place where there are more dots are the compressions. Like we said, the word compression means something is being packed. So if it's packed tightly, then it is an air compression. And where there is less material, it is a rarefaction. Even the word rare implies that there are not many of these air particles. So we have a series of compressions and rarefactions in between until they reach your ear. Now in this case, the amplitude will be how far from its mean position will a particle go to the left and to the right, in parallel with the wave motion. Unlike a transverse wave, like we have at the bottom, where the amplitude will be how far from the mean position it will go perpendicularly to the direction of the wave. At the bottom, to compare with this longitudinal wave, we have a transverse wave, so we can see the different motions. We have the crests, the troughs, the amplitude being perpendicular, and the wavelength being the distance between two troughs in this case. However, for a longitudinal wave, the amplitude is not perpendicular but it is parallel, the wavelength is still the distance between two successive points, and the particles will move parallel to the wave direction, unlike a transverse wave where they will move perpendicular. Moving on to page 15. Let me remind you, in the original set of notes I had sent you, page 15 is not included, so make sure you use today's notes. Make sure you use the notes I have attached with today's assignment. Creating and detecting sounds. Creating and detecting sounds are similar effects, but they are opposite. Whenever an object in air vibrates, it causes compression waves in the air. It could be anything. It could be a musical instrument, it could be your vocal cords, it could be the ruler at the edge of your desk like I showed you in the video that I sent you. Okay? Anything that is vibrating in air is creating a sound. These waves move away from the object as a sound. Vibrations in air will go further and further away from the object as sound. There are many forms of the vibration, some not so obvious, because not all of these vibrations are visible. The back and forth movement of a loudspeaker cone, guitar string, or drum head result in compression waves of sound. What we are seeing here is slow motion footage of a speaker creating a sound. Okay, a pair of speakers creating a sound. Now, unless you set your speaker to an extremely low frequency, a frequency that our ears cannot even hear, okay, we'll talk about this later, you will not be able to see the speaker move like this. That is why this is a slow motion capture of the speaker moving. Okay, the speaker has a mechanism inside of it that causes it to move outwards and back inwards a number of times every second to create the sound that it is being told to make. It could be the voice from a radio, it could be music, it could be just audio signals. So in this case, the back and forth movement is clear. As the speaker cone moves forwards and backwards, it pushes air and causes the vibration in air. And that moving air eventually reaches your ears and you interpret that as sound. We are not going to go into the detail of how a speaker works. However, know that a speaker receives electrical signal from a television, from an MP3 player, from a mobile phone, and it translates that electrical signal into movement of the speaker forwards and backwards, which then results in the sound being generated. With regards to the guitar string, if we refer to last lesson's video, that is extremely clear. The same applies for the drum heads. In that video, which I will link again to make sure that you are understanding what I'm talking about, we see the vibrations there happening extremely clearly. When you speak, your vocal cords also vibrate, creating sound. So first off, sometimes the vocal cords are also referred to as the vocal folds, but they mean the same thing. A very quick example, try placing your hand around your neck and talk. As you talk, you should feel the vibrations in your hand. That is because within your throat, there are these vocal cords, these vocal folds. What we are going to see now is a video showing a human being's vocal cords. The way this video was captured was inserting a very small camera through the singer's nose, a medical camera used specifically for this job and designed specifically for this job. And it goes all the way down to the throat, where the vocal cords are. Now the doctor using this camera is going to ask the singer to sing. And we shall see these parts over here, which in fact are the vocal cords. We are going to see them move.
Good. I'm going to do a lower pitch.
In the second video we're seeing, both of these will be linked. However, this time this is a high-speed video. Okay, so we are actually going to see it in slow motion. As you can see, these folds are constantly flapping against one another, causing the vibration in the air. Remember, for a sound to be created, we push with our lungs. We push air through these vocal cords, and these vocal cords cause these vibrations in the air we push out, and eventually we shape that sound using our mouth, because depending on what shape our mouth has, it makes a difference to the sound, and that is what people hear and people interpret as our voice. Blowing across a bottle top can also create sound. In this case, the air inside the bottle goes in a circular motion, resulting in sound waves being formed. You might have actually experienced this. Whenever you blow air inside a bottle, it does cause a sound. And you might have realized that depending on how much water is in that bottle, or how much liquid is in the bottle, the note that is being created might change. That is because as you blow, the air inside it is moving. However, since it has a fixed shape, and therefore a fixed amount of air in it, it is going to vibrate at a particular frequency. So it creates one note. Wind blowing through trees can also create sound in this indirect way. So as the wind blows through trees, the leaves might vibrate, so they would create a particular sound. Sound can also be created by vibrating an object in a liquid such as water, or in a solid such as iron. A train rolling on a steel railroad track will create a sound wave that travels through the tracks. They will then vibrate, creating sound in air that you can hear, while the train may be a great distance away. Now, last lesson we mentioned that the speed of sound in steel is about 6,000 meters per second. We compared it to the speed of sound in air, which is about 330 meters per second. We said the speed of sound in steel is roughly 18 times faster than that in air. Therefore, theoretically, you can place your ear on a train track and you might hear the train coming by. because the sound is propagating, is moving through that train track. You might be able to figure out whether a train is approaching or not by simply placing your ear and listening for a sound. Now, this idea that a train can propagate sound through its tracks has been used multiple times, especially in movies about the Wild West, about cowboys, that were much more common a couple of years ago. Okay, it's not the first time in these movies that you get the main actor, the protagonist, placing his ear on the train tracks and listening and figuring out whether a train is coming or not. When a sound wave strikes an object, it can cause the object to vibrate. This leads to the method to detect sound, which requires changing that vibration into some other type of signal, usually electrical. The main way you detect or sense sounds is through your ears. The sound waves vibrate your eardrum, which goes to the inner ear and is changed to nerve signals you can sense. Okay, so we've already discussed how our ears can interpret a sound. Those compressions and rarefactions hit the eardrum, which cause those three bones to move. Eventually, they generate a signal that our brain interprets as sound. Now, it is important to note that our ears cannot hear any frequency. Our ears are only able to detect between 20 and 20,000 Hertz. Now, depending on your age, this value might change. It is not exactly at 20 Hertz and exactly 20,000. So the older you get, the limit where you can't hear anything anymore will start to decrease. So when you're born and you have perfect hearing, you might be able to hear up to 20,000, but as you grow and as you hear a number of sounds, your ears immediately start reducing their capability of hearing very, very high frequencies. Now, apart from age, hearing a lot of very loud noises can damage your hearing even further. So let's say if you attend music concerts that are extremely loud, or parties or festivals that are extremely loud, that can damage your hearing. Hunters tend to experience hearing loss because of the loud sound coming from their guns. Musicians that practice in closed spaces with extremely high volume, that also damages their hearing. And if you wear headphones or earphones and you use them at a high volume, that will also damage your hearing, which is why nowadays whenever you try to raise the volume a lot, especially on a mobile phone, it gives you that warning that tells you that you're raising the volume too much. I'm going to link a sort of hearing test for you to try out and maybe compare with other family members, where the sound will start at 0 Hz and go all the way up to 20,000. You should, in theory, be able to hear a higher frequency than people that are older than you. In my case, when I do this test, my hearing stops at roughly 13,500 to 14,000 Hertz. The reason is that I was involved with music for a very long time and we used to practice music in, like I said, in very small spaces with a lot of volume. Until eventually I started using earplugs and ear protection like I should. And let me remind you, it's going to tell you this as well in the video, this is not a sure way to test your hearing. If you'd like to test your hearing, doctors can actually do a similar test, but it is more precise. Okay, this is just to get an idea, maybe compared to a younger brother or a younger sister, or to your parents or older siblings or friends, okay? Try it out and compare, see what happens. If you realize that your hearing stopped much earlier than, let's say, 13,000, it could also be the speakers that you're hearing it on, or your earphones or your headphones, okay? So there are a lot of variables, and don't worry if the value you get is not that great. Okay, it's not a scientific test. To get an accurate result, you should do this test with a doctor. Continuing on, you can also feel sounds. Stand in front of a stereo or a hi-fi loudspeaker on at full volume, and you can feel some of the vibrations from the music. Now, if you are going to try this, I would suggest you protect your ears or cover your ears. However, the music or the sounds that we feel, that we can feel literally in our body, generally tend to be lower pitched sounds. So if you hear any modern electronic music, for example, to test this out, what you will feel in literally vibrating inside your body, if the volume is loud enough, would be the bass drum, the kick that keeps the beat. There are mechanical devices that detect sounds, such as the microphone. The sound vibrates a membrane, which we said is a very thin layer, okay, something that is extremely thin, which creates an electrical signal that is amplified and recorded. So originally, we talked about the speaker, and basically we said there is an electrical signal going to the speaker, and it is causing the speaker to vibrate up and down, moving the air, causing compressions and rarefactions in air. Okay? Now how the speaker actually moves, you will learn in year 11. So here we have the electrical signal changing into kinetic energy of the speaker going up and down, and then changing into sound energy that you can hear in the air that is vibrating. In this diagram, we have the opposite. We have sounds coming in. They are causing this membrane to move inwards and outwards, and that will generate an electrical signal, which is then connected to a form of device if the intention is to record. Speakers and microphones are built in the exact same way. Just a speaker starts from the electrical signal and generates a movement in the speaker which causes sound. And the microphone starts from the sound, which moves the coil in the microphone, which generates an electrical signal. In class, I actually do this experiment where we send a signal through a speaker and we hear a sound, and then we move the speaker to create an electrical signal. However, that will have to wait until we get back to school.